necessary rubber material.
Are you ready?
Yeah.
Thanks for coming for second seminar talk this week. Meike Hatzel from TU Darmstadt, former member of this class. Very welcome to everyone again. Yeah, please.
Thank you for welcoming me back to visit. I'm very happy to be here. I'm presenting joint work with Marcin Zajanski, Karolina Okasa, and Michał Pilepczuk on a width measure for directed graphs called directed tree-cutwidth. And I want to start with a little bit of overview that is on general structure that we can get by excluding things in undirected graphs. So it turns out in undirected graphs we can exclude a bunch of stuff and then get different forms of tree-like decompositions. So Robertson and Seymour showed that if I exclude some graph as a minor, then I can get a tree-like decomposition in which every back is almost embeddable. I can write that. Like that, maybe. If and so our width measure is more about things with edges than things with vertices, so it's more in the line of undirected immersions, or a generalization of undirected immersions. And in the undirected world, if we exclude an immersion as a graph as an immersion, then we get a tree-like decomposition in which every back has almost bounded degree. And if we exclude something that is called a topological minor, which is somehow in between these two things, then we get something that has both kinds of backs. So every back is either of these two kinds of bounded embeddable, like almost embeddable or almost bounded degree. And to get these kind of structures nice, and at the base of a lot of these structural insights, there is something called a grid theory. What I will present today is also a grid theorem for this width measure directed tree-cutwidth. So we also get a tree-like decomposition for directed graphs, excluding certain specific structure, a graph that causes a lot of, and contains a lot of structure. So a grid theorem is we exclude not just any graph, but a specific graph that witnesses a lot of structure, and then we get a stronger tree-like decomposition, one that has bounded size of backs. So let me get rid of this. Like I said, we do this for directed graphs. On directed graphs, we have a grid theorem already for something like we call butterfly minors. This is due to Stefan and Kenichi Kawarabayashi. And this is basically a generalization of the grid theorem that is in the minor structure for undirected graphs to directed graphs, and is for something that we call butterfly minors, which is a version of minors for directed graphs. And it states that that there exists some function such that for all digraphs we have D contains a large cylindrical wall as a butterfly minor, or D has bounded directed tree-width. Most f of k. So bounded in some function of order k. So, and the cylindrical wall is something that is a directed version of a grid. Something like this. And so on. So basically, closed cycles like this. So, and this witnesses a lot of structure, contains a lot of graphs as butterfly minors, and is not only forces the width measure of directed tree-width to be large, but also if I have a graph of a digraph of large directed tree-width, I always contain such a structure as a butterfly minor. And it turns out that the cylindrical walls are also the right obstruction to our width measure. So the directed tree-cutwidth is also forced to be large by this same class of graphs, cylindrical walls. But like I said, we rather work with immersions than with minors. So in our case, we talk about containing a directed graph as an immersion. And while I didn't define butterfly minors in detail because we don't actually work with them, but just for context, with immersions we really want to work. So we say a graph H is contained as an immersion in the digraph D. If I can map the vertices of H to the vertices of D injectively, and also I map the edges of H to edge disjoint paths in D. And if I'm at the edge AB, I map it to a disjoint path from phi of A to pi of B. So the path starts in the vertex that the vertex A is mapped to and ends in the vertex that the vertex B is mapped to, and they have to be edge disjoint. So because we care about edge disjointness and not vertex disjointness in general, we do allow multi-edges between vertices, because now I can actually use several edges between vertices, and it makes a difference whether I have one or two. In the vertex disjoint case, this really doesn't make a difference, so normally we just work with simple graphs. What we still don't allow is loops, we don't have loops. So multi-edges yes, loops no. So as an example, if I look at this graph here with vertices A, B, C, D, I can now map this as an immersion into the following graph. Which kind of structurally looks very different by mapping A here, there, C here, and D here. And we use very much that we allow the edges to be edge disjoint path and a vertex disjoint path, because actually all the paths that that the edges are mapped to walk through this single vertex on the middle.
Are you going to do weak immersion or strong immersion? Or do you allow your paths to go through the image?
No, we don't. Yeah. So this kind of already suggests that in order to immerse a digraph, I can basically take a star with enough leaves for every vertex one leaf, and then if the degree of the in the star actually is at least the minimum degree of my graph, I will always be able to immerse it. So it suffices to immerse this wall if I have a large enough star in which all the degrees are like at least 3. I just need in and out degrees 2 often enough, because in the wall every vertex has in degree 2 and out degree 1, or out degree 2 and in degree 1. So if I want to immerse a large wall, it also suffices to find a star with a lot of vertices that have 2 edges to the center and 1 out, and enough vertices that are the other way around. And any digraph of degree 3 I can immerse into this. So this motivates our definition of onions. So this we call an onion, which has a tip and a root, and 2 edges from the root to the tip and 1 back. That's called an onion. And this is called an onion star. So a center vertex, that's the tip and the root of enough onions that are otherwise of disjoint vertices. And if I have a large enough onion star, I will always find my large cylindrical one as well.
I see, so that picture is onion star.
This picture is the onion star. Yeah? And it's just a lot of onions in which I identify the root of half of them with the tip of the other half of them, basically, into one single vertex. Yeah. And I get that this cylindrical grid, which I call like this, cylinder with a K in the index, that's a cylindrical grid of order K. This immerses into an onion star. Of order K squared. Okay. So I want want to talk a little bit about directed cuts, because the way we work with directed cuts is slightly different than it usually is. So normally we measure directed cuts by, so a cut is a partition of the vertex set into two disjoint parts, and we measure such a the difficulty of such a cut, or the order of such a cut, by the smaller direction of how many edges cross from one side into the other. Then one can work with cuts, like if they cross two of these cuts, then we can uncross them and get some kind of submodularity properties of two such cuts, right? So if I want to build decompositions of graphs, then I can take cuts across, uncross them, get laminar families and stuff like that. But in our context, it makes sense to measure cuts slightly different. So if I have a cut like that, I don't look at either direction of the crossing edges, but I look at how many edges do I need to hit all the crossing cycles. And that makes a huge difference. I could, because such a hitting cycle, I could hit the cycle somewhere here. So somewhere with an edge that is very far away from my cut. So it's a far less local kind of measuring this. So so this is called the width of the cut, and this we call the porosity of the cut. So this, if I now look at two cuts, I have the advantage of kind of symmetric image way I look, right? I don't have that with the width, basically one side is bounded, the other side could, other direction could have a lot of edges. But I do not have these kind of nice uncrossings. So if I have that this has width k and this is width k, and these are kind of smallest cut, then still this can be of size 2k and I can't do anything about it. But this now holds for all four sides. So both of these cuts being small, I still get that all these four cuts that I can get from uncrossing are also kind of small still. I don't get tight bounds, but I can still bound the behavior in this way. And
I have to. So what? So for this corner, you're
yes,
thinking of the hitting set for the cycle crossing that corner, right? So
yes,
So
exactly.
it could stay on the left hand side, right? So you might have a.
Yeah,
Oh.
but so I do have basically a hitting set for all cycles that cross this cut, and I have a hitting set for all cycles that cross this cut. And if I take both of them together, right, there will be a hitting set for all four corners.
I see. Okay.
So I have this blow up because I have to kind of keep like I only, in the worst case, I have to actually keep both the full hitting sets.
So this
But I
hitting
get
set
some
doesn't have to be inside. Or
Yeah, it's not
outside.
like a proper
I see.
submodularity or anything, but
Uh-huh.
about this cut here, if I look at this measure, I don't get any information. I don't, like, this might be of unbounded width, but for the porosity I do get that I get some information for this cut as well. So in some sense it's less well behaved because I get less tight bounds for things, but I do get this extra uncrossing property, which is kind of nice. So also what we want to maybe quickly see is if I take a family of laminar cuts in a graph. Laminar means they don't cross, so I get that one side is completely contained in the other. then this always gives me some kind of tree structure on the graph. So some kind of tree partition of the graph. And similar to that, we measure difficulties of cuts via this porosity property. We also measure the degree of vertices with respect to cycles. So the degree of a vertex, usually, even in directed graphs, is like either the number of out edges or the number of in edges or the sum of both or the maximum of both or the minimum of both. But in our case, there's a lot of options in directed graphs on the degree of a vertex. And we take neither. We take a completely different one, which is similar to the porosity, the maximum number of edge disjoint cycles through this vertex. So if I have bounded degree in any of the traditional senses, right, then I will also have a bounded cycle degree, because I only have 3 edges to go out of a vertex. Then I can also only pack at most 3 edge disjoint cycles leaving this going through this vertex. But I could have potentially very high traditional degree, but actually small cycle degree still. So, as I said, we want to define a width measure, and that's actually the most technical part of this result, that kind of describes or corresponds to like cylindrical grids as immersions. And the maybe first naive approach would be, okay, maybe we try something similar to how a directed treewidth is defined. Directed treewidth takes a partition, like a tree that has backs mapped to its vertices that build a partition of the entire vertex set. And then we bound how many things enter or leave some subtree. So we kind of have between 2 parts, if you have an edge, some edge guard that controls how many vertex disjoint ways I can get from one to the other. So a kind of naive way of saying, okay, if we now want to work with immersions and kind of edge disjoint things, what if I now take here instead some kind of edge interaction controlling way of this, and ask for a partition where all the cuts induced by edges in my tree actually give like bounded porosity. That would be a question, like maybe that's just enough, right? Turns out this is not restricted enough, because now if I look at my onion star, I can easily decompose it using something like this, by basically taking a star and taking every vertex as its own thing, right? The center goes in the middle, and then all the edges, all the cuts given by edges will cut through such an onion, so they're very restricted in how much can happen. There's like, in one direction, even only one thing. There's one crossing cycle. The porosity of this is small, so I have a nice decomposition, but arbitrarily large grids still in it as immersion. So the next idea would be, okay, so if the star causes a problem, maybe if I also say the degree in my decomposition has to be bounded. So let's take a ternary tree and restrict my decomposition to be, okay, I don't only want a tree where all the cuts somehow given by edges have small porosity, but I also want this tree to be of degree 3. Then I run into the problem that now I cannot decompose this anymore and stick to small width, right? So this problem I now have solved. The problem is now I got too restrictive, because what I can also not decompose anymore is just a star with always one edge there and back. This does not emerge anything interesting, but now I fail in decomposing it. So this will cause large drift without actually containing it. So we have to, with our in our tree, kind of restrict the overall interaction of the back with the outside, but we have to be kind of able to distinguish between this star and an onion star. So it kind of makes a difference whether I have like two edges in one direction and one back. This is actually quite similar to the undirected version of tree-cutwidth, because this also makes a huge difference between there being two vertices with just two edge disjoint ways to get from A to B, or the thing that has three. So for undirected immersions, a star that has a lot of these three things also immerses a lot of things, while a star with just two edges does not. So we need to control this, but we notice we only need to control one kind. So if I look at the back, I don't want too many onions leaving this bag. Kind of base in this bag, going out, coming back. If I control all of them, good, but I actually don't need to, because if I had just a bunch of onions like this, which let's call them an out onion from this bag, but don't have any in onions, or only few of them, then this still doesn't allow me to build a large grid. So actually I only have to control one type of onion for every bag. I don't have to actually control all of them. So I gave you a little bit of intuition what we try, or what the demands on the decomposition is. So let me define the actual directed tree-cutwidth that we in the end like ended up with. So we have a tree and three functions. No demand on the degree of the tree at all, it's just a tree. We have beta, which, as in a lot of other decompositions, gives us bags for every vertex. So it's a function that maps the vertices of the tree to vertex sets in D, and we want this to give a near partition. So no vertex lies in two different bags, but empty bags are allowed. We have gamma. Gamma are what we call edge guards. They map every edge of the tree to a set of edges in D, and they're kind of similar to what guards are in directed treewidth, just now as an edge set. And these witness that the cuts have small porosity, so they hit all crossing cycles. And finally, we have theta, which are onion guards. They map every vertex to an edge set that is now a hitting set for all out onions or a hitting set for all in onions. Yes?
Could I force you to use a brighter green?
I don't think I have a brighter green. I can use a different color though. I have a lot of colors.
Thank you. A lot better.
Cycles. It's all in or all out onions. So, but for every bag, the onion guard has to decide which kind of onions it hits. So now we get some kind of tree-like decomposition blobs. We have a guard on every edge, and then I also have some kind of extra edge hitting set assigned to every bag that hits all out or in onions. So basically each of these kind of has a label in or out which says it hits all the in or all the out onions of this bag. And an in onion or an out onion of that bag is either very obviously something that has its root in, the tip out, and then is connected like this, then it's called an out onion of the bag. But we also consider if I have something that lies somewhere here and it has, let's do this in color, so it has its tip here and the root there, and in order to get from the tip to the root it has to walk through the bag, then it also counts as both an in and an out onion of this bag. Because the onion can, it looks the same, right? But
So when you say onion, it's not like 3-edge graph, it's a 3-path, or
yes,
yeah,
yeah.
okay.
So it's basically an immersion model of this. Okay, and this decomposition has a width. The width is the maximum size of any bag, edge guard, or onion guard. And so all of these things have to be kind of small. And then the directed tree-cut width of a graph is the minimum width over any decomposition of this kind of the graph. And if one thinks about it a little bit carefully, then it's also quickly clear that if I have a cylindrical wall, then it forces this width measure to be large. Because whichever way I cut through the cylindrical wall, I always have a lot of onions that cross between the two sides. Alright, so the remainder then, and therefore our main theorem, is to prove that the other direction also holds. I can do this. So. So either I contain an order K cylindrical wall as an immersion, or the directed tree cut width, this is how we write this for short, is upper bounded by this function in K. So now
Some very stupid questions. Your tree is unbounded degree?
yes, the tree is
And-
unbounded.
And the guards, you're just trying to wrap my head around how by the guards are incomparable, but it's like, okay.
So-
Okay, if you have unbounded degree, you have to hit all cycles on every edge,
Mhm.
but then you also have to hit.
So the backs are partition, right? So that kind of forces these cuts to be somehow laminar on the entire graph, right? Because you can't, every edge in this decomposition gives you a split of the graph into a disjoint vertex set. All the things on the backs on the one side and all the things in the back on the other side, and that's the cut we consider. And for this, the guard has to be a hitting set of all crossing cycles.
Right. I think I was just making a very silly mistake. If your tree had bounded degree, the edge guards would have been enough, right? Is that
Yes, but then it was too restrictive.
Yeah, okay.
Because then
Yeah.
we could, because we couldn't decompose things anymore that actually do not contain a lot of structure. Okay, good. I promised that the talk is about onions and potatoes, and so far I have not mentioned any potatoes, so let me rectify that. As a first step, so what we're going to do is, if D does not contain a wall as an immersion, a large wall as an immersion, then we can decompose the graph. So we need, for a given graph that we are promised does not contain any of these cylindrical grids as immersions, then we have to be able to decompose it. And we do this, step one, by using something that we call a K-potato decomposition. Yes. So K-potato decompositions, yet another decomposition, so it's a tree and it has functions. And the way you would actually expect, so the function better again maps vertices of D to vertex sets of D in a way that it is a near partition. And now we also want, because we have this K, we want this to be K-flow connected. So it partitions the vertex set into things that are connected by a lot of edge disjoint paths. And now this is edges of T to sets of edges that hit again all the crossing cycles. So they we have that the cuts given by the decomposition are already of small porosity. So edge hitting set, sorry, edge hitting set for all crossing cycles. So we have this extra ask that the parts are largely flow connected. We have zero demand on these backs to be small though. K potato decomposition just says I decompose the graph in a tree-like fashion into well-connected parts that are separated from each other by cuts of small porosity.
What is exactly the K-flow connected?
So for any, if I look at a back, for any two vertices in that back, I can find a large flow, so edge connected, edge disjoint path from A to B, and in the other direction, just they might not be disjoint. This I don't know.
Oh, I see. So for any pair XY, you have
Many edge disjoint
edge
paths
disjoint
from
paths.
X to Y, and many edge disjoint paths from Y to X.
And this is all staying in the backup, right?
Well, you don't. You're not really forced to stay in the back, but because you have small porosity, you don't really cannot go that much out of.
wait, is that true? Because your tree doesn't have 100 degree, does it?
Ah, you're right. You're right. Flow connected. I think you don't have to stay
Okay.
in the back.
If you don't have to stay in the back, then what's the difference of just the graph being K-flow connected?
Maybe for two vertices not in the same path.
Yeah, you don't need to be connected to things that are in a different part.
But does it have to stay within the graph? That's the image.
That's the
Or the back
question,
bend?
and I don't think you
Ah.
have to.
But
No, I don't
if
think
it-
you have
oh,
to,
sorry.
but I'm not entirely sure right now. I don't think you have to.
If I make a star with every back having just one vertex, then is it a potato decomposition?
Only if you have cuts of small porosity. So depends on how the edges between these things look. Right, so for the K flow connectedness, yes, if your back is only one single vertex, this is easy to get. But you might not be allowed to make every vertex its own thing because you might have a bunch of things that then go over cut.
I see, so you want this gamma set to have size at most K?
Yeah, so this potato decomposition has a porosity, right? So the porosity is the maximum size over all the gammers, and you would like the porosity of this to be small. And one can prove that there is a function, let's call it maybe different, let's call it potato function or something like this, such that every digraph D has a K potato decomposition of porosity at most potato function of K. A major tool used for this are like important cuts. And you prove it by basically by induction on K. You start with, okay, if I want to just have like one decomposition, I start with like strongly connected components, and then I have that the cuts are actually empty. And the larger I get, I take the K minus 1 potato decomposition that I get by induction, and then take a laminar family of cuts that cuts up every part. There's laminar within this cut, and I do this for every part, getting kind of nice trees for every part. Yeah. But then I have that these cuts are maybe very nicely behaved for this back, but maybe do whatever once they get outside. So the major difficulty is here in the induction step, basically cleaning out these local decompositions and make them attachable to each other so that in the end I can get a decomposition of the entire thing. This is very technical though. But the basic idea is this, and then important cuts allow some kind of uncrossing here, and you do also lose in these cuts because we use the cycle porosity in this, allowing us then though to make some uncrossings that with standard width of cuts we were not allowed to make. Okay. But let us just assume we get our potato decomposition. And once we have a potato decomposition, we can even manipulate it a little bit and make things like root the tree and make the things that are in subtrees of this rooted tree strongly connected. So this is a trick that's also often used for directed treewidth or things that are related to this. So our next step is to root. Okay, look, we first take this potato decomposition. Okay, potato decomposition. Now we root T in a vertex R, and we also make subtree strongly connected. And now we can, for each bag, every bag has a parent and a bunch of children, define something that we call the torso of this bag. So for
Sorry, what do you mean by making the subtrees strongly connected?
that the graph induced by the bags that lie in a subtree, this is always that this graph is strongly connected.
So do you change the decomposition to get these? Or?
You change it a bit, yes.
Okay.
Yeah. So it's not like you immediately get this. You have to tidy up a bit and cut things off each other and rearrange, but you can get this.
Does the width go up a little bit, or?
I think actually for this it does not go up. So you can do this without. But as I didn't tell you what the function in the end is going to be, and the function in the end is going to be very, very horrible. If it goes up by a factor of a bit, then this would also not matter. But it does not. Okay, so now we build something that we call a torso for every bag that we have. And for this bag, let's say letter of V, we build a torso by, for every child of it in the decomposition, adding 2 new vertices and a kind of small fake onion between these 2 vertices. These are called Chekhov edges.
I'm going to be so disappointed.
What is Chekhov?
Wait for it.
Yeah, wait for it. So if I have an edge between a vertex in my bag and some vertex in the subtree, I replace it by an edge from this vertex to the root of that onion instead. If I have an edge out of this child, I replace it by an edge from the tip of this onion instead. And I also keep edges that go between 2 of these. Edges. By replacing this with an edge that goes from the tip of the one to the root of the other. So if I had some path through here, I can replace it by these things. Too many chalk pieces in my hand. Okay. So next step is sorting where I am in my notes. Next step is to decompose torsos, right? If we have our potato decomposition, we have already cuts of small porosity, all good, but we have that our bags are arbitrarily large, and we don't have any onion hitting sets yet. If we look at the torso, then we notice that the only vertices of high cycle degree are original vertices, because the new vertices I create all have either in or out degree 1. So they have cycle degree exactly 1, or at most 1. I could actually also have no cycles through a vertex, just makes it useless. So if I have a vertex of high degree, it will already be in here. But if I have, these are large flow connected, and there is a result by Bourget, Deflin, Okrasa, and Pilipchuk. That gives me, that was over here from 22, that says if I have a set of a lot of vertices that are highly connected to each other, then I find a vertices imply large onion star. Right, so if I have a huge set of vertices that have high flow between any two of them, then I can use this to build an onion star. Which means that actually in this I can also not have too many vertices of high degree. And if I have not too many vertices, period, sorry, right? Because if I have a lot of highly connected vertices, I find an onion star. Means I actually already do know that my bags are small by this result. Because we excluded the large cylindrical walls as immersions. So I have that the bags are small, I have that the porosity is small, so now I kind of want to get onion guards. So what do? I look at the torso and I look at the high degree vertices in it, and I know the high degree vertices already have to lie in the original bag. And now the remainder of the proof basically goes via the number of highly degree vertices that I can have in this torso. If I don't have any high degree vertices, then I can actually do basically a directed tree decomposition. If I have somehow bounded degree, then finding an immersion and finding a minor is very similar. So one can prove that in the bounded degree case, I can just use a directed tree decomposition. So the interesting case is there are high degree vertices in this. And we're going to do the case where we have exactly one high degree vertex. So let's say we have a high degree vertex Z. Now if I can find many out onions from this Z that are based on Z as a root, and many in onions to Z that have Z as a tip, then I can build an onion star. Sure, I have to do some crossing and see that I can actually get them somehow disjoint and everything, but if I have a lot of them, then I can build an onion star. So of either kind, there has to be some kind of bounded number that I get. And this is like within my torso, yeah? This is some torso of some bag. So let's say there is a bounded number of out onions. so I don't have many out onions. If I don't have many out onions, then I can find a hitting set for them. This is also not trivial. This is in a different paper. This it's basically an Erdős-Pozsa result, and I've talked about it here already, not in the seminar, but during the method workshop actually. So this follows from some Erdős-Pozsa on graphs where I pack or hitch things of this kind, like tripods that are from some source to some between some source and some target set. So this gives me that I get this kind of Erdős-Pozsa property for onions based in a vertex, or even in a set. So once I don't have one single degree vertex, high degree vertex, but several, then I can also still use this. And now this already is very much of the shape of the thing we're looking for, right? So this is gonna become our onion guard. And depending on so it might be that I have to also decompose the set further if I have more than just one set, right? So it might be that the set actually, like that this yields a decomposition of the torso rather than directly an onion guard for the torso I already have, right? So these things become onion guards, but they don't become onion guards of my torso towards the rest. They become onion guards for some partition in the torso, right? So for decomposing the torso. So what I end up with is, for my larger decomposition, I now have, once I build the torso, I think this is pink, right? So I can build a torso, and I can decompose the torso. So now I have to kind of make this a decomposition of the actual graph that I have, of the actual bag I have in here, right? So I have here somehow like the extra vertices for all the children. So one step first is to make these auxiliary vertices lie in the same bag, to make it easier to decide where, if I now have the decomposition of this thing here, where I do attach it to the decomposition above. And then where I attach it down here actually does not matter. I can just put the guard that is on this edge together with some guard that I get from the decomposition in here on all the edges down here, and then it doesn't really matter where I attach it there. So there is some technicality, let's say a lot of technicality, going into, now I have decomposed all these parts, now I have to attach these two decompositions to each other in a somehow valid way, and adjust my guards by taking, okay, whatever was the guard here will be added to this, and all the edges down here. And that way I then also get new edge guards for the decomposition here. So the onion guards I get from this argument, the edge guards I get out of the old edge guards, but I have to like take an edge guard for the incoming outside edge as well as some edge guards from inside here. And that then allows me to put it all together and decompose the actual original graph. That's it.
the decomposition in case you don't have a large cylindrical wall?
It's all algorithmic, so there is an algorithm to actually do algorithmically get the thing, but the running time depends on the function, so it's that. But it is like
It's XP or is it?
the function is not an elementary because of this thing. So actually this ingredient here is like some onion uncrossing lemma. It's called onion harvesting lemma, and that's actually and that's actually the blow up and running time and in the function as well. Yes.
Well, we actually prove this if we don't have a large onion star, then directly treewidth is bounded. So instead of the cylindrical wall,
So
just we can say onion star.
yeah, but the cylindrical wall has large directed tree-cutwidth and does not contain a large onion star as an immersion.
But in the proof, we like every step seems to say like there's no large onion star, and then
Except for when we use the bounded degree case, the directed tree width.
So
Right?
that's where
In
that's
that
where-
case, we do not use. We exclude the onion star, but in that case, we actually exclude the wall.
So you can say something about like digraph without having onion star immersion by either having this structure or something, or I don't know.
What do you mean?
I don't know if I wanna have structural characterization of digraph without onion stars
As an immersion.
immersion.
But they can still contain large walls, yeah?
Yeah, so either but
Could be very complicated because they contain large walls. I mean,
Yeah, but they still have a very structured thing in them,
Yeah, yeah.
so. Yes.
You can't just write check-off edges and not use them, right?
yes. I said I would be disappointed, right?
Yeah, so the check-off edges, you need to do this moving. So if you have that your two vertices that were kind of the auxiliary vertices for this child in this new decomposition, and they're somewhere here and somewhere there, right? Then because they were split, there's this onion that was counted in all the cuts between them. So moving it, right, will always maybe bring some onion with it, but it also always removes this onion, and this allows us to, there is already some complexity counted in here. And without it being like that, you would not be allowed to move it without blowing up the porosity of all the cuts between them.
But why check-off?
That's why they are called check-off edges because of the way we introduced them in the discussion, right?
Any more questions? Okay, if not, let's take